Let's start class today by looking at some problems in the section about differentiability and working through some of them to help you understand what the goals are for this section. What does it mean? We did talk last week about what differentiability means. In a nutshell, a function is differentiable at a point if f prime of that point exists. By the word point, I mean number, really. C is some value of x on an x-axis. Is f differentiable at c? It will be if f prime of c exists, according to the limit definition of the derivative. Where I am assuming f is defined near c, it's not an endpoint of the domain, so that limit in the definition of the derivative is two-sided. But you should be able to do problems that are purely graphical as well, related to knowing when functions can fail to be differentiable at a point. I mentioned there's a theorem that says if a function is differentiable at a point, it's also continuous there. Therefore, if it's not continuous at a point, it's also not differentiable. So for this graph that you see right here, you can see it's not continuous at x equals 1. You've got a jump discontinuity there. Therefore, at x equals 1, that is a point where it's also not differentiable. The theorem says if the function is differentiable at a point, it's also continuous there. Therefore, if it's not continuous, it's also not differentiable, because if it was differentiable, it'd be continuous. Oh boy, around and around we go with the logic, but that is the correct logic. Anyway, in a nutshell, it's not continuous at 1, so it's not differentiable there. It's also not going to be differentiable where there are corners in the graph. Is that a corner right there? Yes, it is. So it's not differentiable at 2. Is this a corner right there? Yes, it is. So it's not differentiable at 3. How do you tell if it's a corner or not? Well, does it look like a corner or not? Sort of the quickest way to say it. If you want to be a bit more technical about it, does the slope from the left equal the slope from the right as you approach the point, or are they different? They are different here. Question? I said differentiable means the derivative exists. You got, at that point, if you imagine tangent lines as you approach the point from the left, they all have a slope of 0. But the tangent lines as you approach the point from the right have a slope that's positive. Positive 1 or so, it looks like. On the other hand, at this point, as you approach the point from the left, the tangent lines look like they all have a slope of positive 1. But as you approach the point from the right, the tangent lines head toward a slope of 0. 1 does not equal 0. Different slopes as you approach the point. It looks like a point of non-differentiability, and it is. You also want to watch out for points where the tangent line appears to be vertical. The main example from last Friday that you should know for the exam, maybe a true-false question, is the cube root function. We saw the cube root function at 0 had a tangent line that was vertical actually at 0. As you zoomed in closer and closer to the origin, the graph looked more and more vertical. That's an intuitive description, not a proof, but an intuitive understanding of why the tangent line at the origin for the cube root function is vertical, and therefore, since vertical lines have infinite slopes, the function is actually not differentiable. This graph doesn't have a formula, but it does look like it's got a vertical slope at one point right there when x is 2. So even though the graph is smooth, you might say, now no corner there, the fact that it's drawn in such a way to look like it has a vertical tangent at that point, if you zoom in closer and closer to that point, it's going to look more and more vertical, is enough in this purely graphical problem to say, no, it's not differentiable at 2. Even though there's no discontinuity there and there's no corner there. If it's a purely graphical problem with no formula, approach it that way. There's also a corner, it appears at 4. That's also a point of non-differentiability. It was just asked a minute or two ago, can it be the case that you have a graph that changes so rapidly that it looks like there's a corner, but there's really not? And yes, that can happen. An example of that is problem number 12. 12 says, look at the graph of this function. F of x equals weird function, x squared plus 0.0001 all to the 1/2 power, which means really the square root of that whole thing, right? Half power means square root. There's the graph. Hey, it looks like it has a corner at the origin. But is it really a corner? It must not be. Question? That was what I was saying a minute ago. In these purely graphical problems, I said, if it looks like a corner, it is a corner. If it looks like it's a vertical tangent, it is a vertical tangent. But then I was warning you that in problems like number 12, when you've got a formula, you've got to zoom in. In number 12, we got a formula. The book shows you, hey, this graph makes it look like there's a corner there, but it's deceiving. You have to be more sure by actually zooming in. So you'd want to take your calculator and you'd want to type this function in. I could do it with a 1/2 power, but I could also do it with a square root because 1/2 power means square root. X squared plus 0.0001. Is the textbook trying to trick you? Very possibly they are. Not for the purposes of just purposely trying to trick you, but because they want to test your understanding in the way that I'm explaining right now. You can't tell necessarily. Well, graphs can be deceiving is the point. You have to know for sure, either by symbolic calculation or, in this case, by zooming in further and further. I'm pretty close to the origin here as it is. Let's see if it looks like it's corner on this scale or not. I don't know if it will be. Let's see. Looks pretty corner-like, though maybe not as much as the book's picture, at least. Let's zoom in closer. Negative 0.01 to positive 0.01 for x. I don't know if you noticed there, but the graph actually was not going through the origin. So as I zoom in the y direction, I probably want to be a little bit above the origin, actually. Let's go negative 0.01 to positive 0.02, maybe. So I'm a little bit above the origin, especially in the y direction. Yeah, it doesn't look like a corner anymore. This function actually is differentiable at x equals 0. The reason this is deceiving is because, well, pictures can be deceiving. Graphs can look different on different scales. Even when a graph looks like a V, maybe if you zoom in near the bottom of the V, it doesn't look like a V anymore, and that's what happens with this graph. As opposed to the absolute value function, if I do the absolute value function here, going into the catalog, where's my catalog button? Catalog ABS of x, and graph that as well, that still looks like a corner. And it'll look like a corner no matter how close I zoom into the origin there, as long as I zoom in the x and y directions at the same rate. It'll continue looking like a corner. So that truly is not differentiable, okay? So there is a point to these problems, not just to trick you, but to make sure you understand the subtleties. Math, and especially calculus, is full of real subtle things. You can understand the big ideas of calculus at a conceptual level, but still be misled to misunderstand some subtleties. Those subtleties are worth knowing about to truly understand the subject at the best possible level, because these subtleties come up sometimes in applications. As an example of an application, take a look at number 13. That doesn't look like such an easy problem. It's more scary looking than it actually is. The acceleration due to gravity, little g, varies with height above the surface of the Earth in a certain way. Wait a minute. That's a confusing statement. Didn't my physics teacher tell me little g is constant? No, it's not constant. Your physics teacher lied. Really? Well, they fibbed. I hinted at this a week ago or so, I think. Anyway, little g, the acceleration due to gravity near the surface of the Earth, is actually not constant. If you go to the top of a tall mountain, it's a little smaller, maybe 9.7 meters per second squared instead of 9.8 meters per second squared. That's because it's really a function of how high you are above the surface of the Earth. Little r here, yes, is the distance to the center of the Earth, actually, instead of the surface of the Earth here. It's really a function. It's not constant. So why do we treat it as a constant in physics? Because it's a good enough approximation for most applications. That's why. That's what mathematical modeling is all about, is trying to get away with the simplest math you can to get accurate predictions. If they're not accurate, then you try to make a more complicated model. Even with free fall near the surface of the Earth, it won't be an accurate model if you're using a feather instead of a rock, right? Feather is not going to fall toward the ground according to the ordinary model because of air resistance. A rock, that's a better approximation, the ordinary model. So you have to think about making your model more complicated when you have to deal with other things like air resistance, or like if you are up on a tall mountain, or if you're sending a rocket way up in miles into the sky and letting it come back down. You have to deal with the fact that little g is actually not constant there if you want an accurate enough model. So here's a seemingly pretty complicated model for how little g depends on r, the distance from the center of the Earth. Little g is really a function of little r being the distance from the center of the Earth. But you have these other letters as well. Capital G, capital M, capital R. What are those things? Capital G is called the gravitational constant. What's that? In standard units, it's a really, really tiny constant. I don't remember the exact value, something on the order of 6 times 10 to the negative 11th. Its units are really weird. It's something that Newton hypothesized is a constant related to gravity that gets essentially transmitted over the entire universe. Like that planet that's 1,000 light years away in that solar system does affect your position, or your, what am I trying to say? It affects Earth, okay? It affects how Earth moves with a slight gravitational pull. Now, that gravitational pull is so small, it's probably not measurable. But in theory, it exists, okay? And little g is related to that, or capital G is related to that. Capital M is the mass of the Earth. Capital R is the radius of the Earth. Do you need to know what capital G, capital M, and capital R are to do this problem? No, you don't. They're just constants. Don't worry about them. Well, if they're just constants, how in the world can you possibly do part A? Sketch a graph of little g against R. By realizing that even though you don't know what capital G, capital M, and capital R are, they are constants. And so these two equations in this piecewise formula are functions of little r. And the first one, when little r is less than capital R, is a linear function of little r. Little r is to the first power. And in fact, there's no plus constant here. Its graph goes to the origin. And it's linear. It's got to be straight with a positive slope. Capital G, capital M, and capital R are all positive numbers. It's a straight line with a positive slope. In fact, capital G times capital M over capital R cubed is the slope of that line. Who cares what it equals? It's the slope. Once you get to capital R, though, then this is a r squared in the bottom of the fraction. It's no longer linear. It's a constant over r squared. The graph's got to be decreasing over here. And not along a straight line. Graphing something over x squared gives you graphs that look like that. Decreasing and concave up, in fact. And I'm drawing this in such a way that I purposely made these separate here, separated. But should they come together, should this be a continuous function? It actually is continuous, and I hope that makes some intuitive sense. And in fact, if you plug in little r equals capital R into either one of these expressions, you get the same value. If you plug in little r equals capital R right there, one factor of capital R cancels, leaving you with capital G times capital M times capital R over capital R cubed. Yes, one factor of capital R cancels, leaving you with capital G times capital M over capital R squared. And if you plug in little r equals capital R right there, you get the exact same thing. That essentially, verbally, is a proof that the left-hand limit and the right-hand limit as little r approaches capital R, either from the left or right, is the same, equaling that. That's the value of this function when little r equals capital R. But look, this one's straight with a positive slope, whereas this one is decreasing with negative slopes, including a negative slope as you approach capital R. This function is not differentiable at capital R. These comments are related to parts B and C. Is little g a continuous function of little r? Yes, because the left and right hand limits as little r approaches capital R both equal the same thing. The one-sided limits exist and are equal. Is it differentiable? No. It is differentiable everywhere except when little r equals capital R. There's a point of non-differentiability. Is that a proof? Not really, but it's a good enough reason for our exam. Now, would I give you a problem this complicated on your exam? Probably not quite that much with so many letters all over the place. But I wouldn't rule out a problem like this, perhaps. Let's look at this one, too. An electric charge, or more physics here, Q in a circuit is given by this function of time. This is a piecewise function as well. There are still unspecified constants in this formula, C and capital R. Just tells you those are positive constants. If you know about electronics, I think C is the capacitance and R is the resistance, perhaps, of some circuit. Don't worry about it. You don't need to know what they are. The electric current, I, is the derivative of Q with respect to time. Do you need to understand circuits to do this problem? No, not really. You need to understand functions and functions formulas and graphs, including the piecewise formula. In this case, Q is a function of t. This is saying Q is constant when t is less than or equal to 0. Some evidently positive constant value, like that. Once t becomes positive, then it's exponential decay. R and C are positive constants, so negative t over R times C is effectively a negative constant times t, or t divided by a negative constant. That's exponential decay. As t increases, the graph looks like that. The values of R and C do affect how fast this goes down. How fast is the decay? But you don't need to worry about what R and C are. Is the charge continuous? Yes. What's the reason? Once again, the left and right hand limits of this function as t approaches 0 in this case are the same. They're both C. Certainly the left-hand limit is C because the function always equals C when t is negative. As t approaches 0 from the right in this formula, this expression e to that power is approaching e to the 0, 1. As t goes to 0, C times 1 is C. The left and right-hand limits are both C. That's enough to say the function is continuous at C, and it is defined to equal C at t equals 0 as well. Do you think the current is defined for all times? Well, the current is the derivative. Looks like we got a corner in the graph. And yes, it is a corner. It's not differentiable at t equals 0. The slope here is 0. The slopes of tangent lines here are not 0. They're all negative, and they get more and more negative, you might say, as t gets closer and closer to 0. The slopes from the left and slopes from the right are not equal. Therefore, this is a true corner. You're not being deceived. It's a spot where this function q is not differentiable. And therefore, that means I, the derivative of q with respect to t, does not exist. What does the graph of the current look like? I being dq dt. Well, it's 0 over here where Q has a slope of 0. It doesn't exist at t equals 0. And when t is ever so slightly positive, it jumps to a negative slope. And it stays negative for all positive values of t, though those negative slopes get closer to 0. This would be a graph of the current versus time. It doesn't exist at t equals 0. Is that what really happens in an electric circuit? You might argue it might be physically impossible, but from a mathematical modeling perspective, it's probably the best function to use. What's really going on here in the circuit? Evidently, it's like turning on a light. The current, there's no current until t equals 0, when all of a sudden there's a negative current that goes up towards 0. You might wonder, how can there be a negative current? I don't want to get too deep into electric circuits, but suffice it to say, it kind of works like this. Current is imagined to flow from positive charge to negative charge. So it's flowing from positive charge to negative charge. If it flows backwards, that's called a negative current. But it gets even more weird because positive current is actually opposite direction electron flow. Okay, I don't want to say any more than that. If that confuses you, as it very well might, ignore it. If you really like electric circuits, maybe you've studied them already, you know what I'm talking about. It's weird, it's confusing. Don't worry about it. You don't have to understand electric circuits fully to understand that this function is not differentiable at 0. There's a corner in the graph. Okay, so I'm saying these things to make you realize, yes, there is a physical reason behind it. And if you know the physics, you can understand it better. But you don't have to understand physics to be able to do the problem.